For your exam on Friday, I was telling this to the people that were here. The exam is going to be open around 8:30 in the morning, and it's going to be closed Saturday, close to midnight. So the way it works is that you can start your exam anywhere in that window. And once you start the exam, you're going to have around 2.5 hours to finish your exam. I don't know exactly the time because I haven't finished doing the exam. So once I finish it, I will know better. The exam is gonna be 5 questions, and it's gonna be a mix of concept questions and problems. On your exam, you can, or yes, you can write down the answer. But I'm going to ask you to upload the worksheets that you have done to solve those problems. So the answer itself is not going to be enough. That's only like 20% of the grade for each problem. The big chunk is the actual worksheet. So you may have an idea of what will be your grade. You will know if your problems are correct or not at the end of your exam, but you won't have a final grade until I go and review your exam, your worksheet, and the concept questions that you answer. So I'll probably gonna have your grades by Wednesday next week, and that's it. Obviously, you can use textbook, but you're not allowed to consult anyone or ask questions to anyone. Okay, makes sense? Yes, Trent.
Do you know how many questions, on an estimate?
Around 5, a mix of concept questions and problems. I still haven't decided how many of each. Probably 2 and 3. 2 concepts, 3 problems. Yeah. Yes.
It's going to be a mix of problems from the start to
Yeah. So the problems are going to be covering everything that has to do with forces, equilibrium, torques, and balance. Yeah, well, equilibrium, balance. Yeah, those are basically the equilibrium is like the big topic. It's just the difference of equilibrium that we've been talking about. Okay. Now, so today I have a couple of new material that I would like to go through and I would like to show you, but I want to see if there's any questions about the homework. So I know Paige,
That's an understatement, but we can see. I wanted 68.
68. So 68 is the spine. That was the last one?
Yeah.
Okay. Okay, so we have a person. I'm gonna put it on the image so everybody remember. Okay, let me share this thing. Okay, Aubrey, Samantha, Mark, can you guys see this textbook?
Yeah, I can see it.
Thank you. Okay, so this is the problem this is a problem that we're talking. So we have a person that is flexing his at the waist. So he's doing this 30-degree angle with the horizontal, and we are looking at the force on this muscle over here. Okay, so the advantage of this problem is that it already gives you the free body diagram, or it gives you the beginning of the extended free body diagram. So you're just gonna work with this one. Okay, so we're gonna have the pivot point. We have the first center of mass. This is the center of mass of the torso. And here is the center of mass of arms and head. And we have this spine muscle, and then we have a couple of distance. And I think one of the problems that creates one of the problems in this particular text is that instead of giving you values for the distances, give you ratios. So we have the length of the spine, which is going to be L. The center mass of the torso is going to be at 1/2. 1/2 of the torso. The insertion point the insertion point. So this distance over here is 2/3 of the total length. And what else do we know? Oh, this angle is going to be 12 degrees. And this angle over here is going to be 30 degrees. So it looks a little bit very crowded, but I think that's it. And what else do we need? We have the weight. So we have the weight of the torso. And the weight of the torso,
32, 320.
320, thank you. 320 newtons. And the weight of the head is half of it, right? 160 newtons? Mm-hmm. Okay, and that's it. And what we are asking is what is the force in the muscle? So we want to find out this force over here. So this is the force of the torso, the weight of the torso, the weight of the head. Okay, there is another force that is going to be here on the spine, but because it's at the pivot point, it's not going to create any torque. That's why they're not drawing it. But here, there's going to be a reaction force. And that one actually is quite important when people get some injuries in the back, is precisely because of that reaction force. That's the force that compresses the spine. So if you have a big reaction force, is that the compression that can break or dislocate your discs. But right now, I'm just going to solve for the force of the muscle, okay? So, and this is what we want to know. So again, we have 3 set of equations that we are trying to solve. That it's gonna give us a static position and the system to be not moving. So I'm gonna start with the torques, okay? So on the torques, I'm gonna have the torque of the muscle plus the torque of the torso plus the torque of the head. That's gonna be equal to 0. We have a torque of the reaction force, but again, that's gonna be 0 because that force is going through that pivot point. It doesn't create any torque. So the torque of the muscle, if you see the spine and this muscle over here, this is 12 degrees. So remember, the angle that we care is the angle between the axis of rotation, this axial radial line, and the force, the one that is less than 90 degrees. So this 12 degrees is actually the angle that we need. We don't need to do anything else. So this force is going to be the force of the muscle times the distance, which I know is going to be 2/3 of the length, times the force, sine of 12. Okay, that's going to give me the torque. Now, if you see this force is rotating, it's going to rotate the spine clockwise, counterclockwise. So it's going to be positive. Okay. Now, for the torque of the torso, what we have, it's something like this. Okay, I know that this angle is 30 degrees. So this over here has to be 60. Okay, so again, the angle that we care is you have the axial radial line and the smallest angle, or the angle less than 90 between this line and the force. So we're going to be working with the 60-degree angle. So this is rotating clockwise. So this is going to be a negative torque. So the distance is going to be 1/2 of L. The force is 320 newtons. And the angle is going to be sine of 60. Okay? And for the last one, it's going to be something similar. It's going to be also be negative. The angle is still going to be 60 degrees. And it's also going to be negative. So it's going to be L times 160 sine of 60 equals 0. Yeah, makes sense. Now, notice how every term in the left side of the equation is multiplied by L. So you can divide the both sides of the equations by L, and then the L's are going to cancel. So it really doesn't matter the length of the spine. What it matters is the relationship between the length and the insertion points and the locations of the centers of gravity. So these are going to cancel. So we can rewrite this equation, and we're going to have 2/3 Fm sine of 12 minus 1/2 320 sine of 60 minus 160 sine of 60 equals 0. Okay, and from here I'm just going to do a little bit of algebra. I'm solving for this force of the muscles. I'm going to pass these terms that don't have a mass. I'm going to put it on the right side. So here I'm going to have 2/3 sine of 12. This is going to be 112 320 sine of 60 plus 160 sine of 60. Okay. 1/2 times 320, that's going to be 160. So notice I have 2 times the same terms. So this will be 2 times 160 sine of 60. And here we have the 2/3. And from here I can solve for the force. Sine of 2. These are going to cancel. And
I have a question.
yeah,
Why is there now like 2 160s? Like what happened to the 120?
120.
Yeah. Or the 320?
So this 320 is multiplied by 1/2 over here.
Got it.
Yep.
Yep.
So I get, rounding up, I get 2,000 newtons. I don't know exactly what is the answer in the book. Is that, Ian, is that the right answer? That's what you got? So we can say that is the right answer.
Yeah.
Yeah?
It's just under.
Yeah, just a little, 1,999.37.
Yeah.
Yep. Yeah, makes sense. Now, we can also, so this will be the force on your muscle, in this muscle. Notice that one part of this muscle, this force have two components, and I'm gonna draw it over here. So you have force going down, force going down. You have this force. Each one of these forces have two components. One that is perpendicular to the spine. Okay. And there's another force, and this component that's perpendicular is the one that is causing that rotation, is causing that torque. But there's another force that is going to be parallel to the spine, and all these forces are going to point in towards the base of the spine, to the joint. So you're going to have a reaction force here that has to match all these forces over here. So this reaction force is going to be way, way high. And that's the force of compression. That's the one that hurts people. That's the one that dislocates shoulders, or dislocate discs on the spine. We're not going to calculate it right now. I will let you as an exercise for the reader. You can give it a try. If you can try to solve this one. But this force is actually quite important. That's the one that actually causes injuries. If you don't have a strong spine muscle, your this will be compressed too much. Okay. Any other questions about the homework? No, I think you had a question.
Can you do the first one,
Number 9. Oh. Okay, so here we have two objects, two pieces of wood. This one has a length of 2 meters. This one has a length of 1 meter. The mass of this guy. Yeah.
Not the one I had.
Yeah, the two objects of figure 8.9 are balanced on the
Oh,
pivot.
no, you're right. It's a good thing we looked at that because I was doing the wrong one. Okay.
So when I'm asking the problems, do the problems from the problem section. At the end of the chapter, you have two sections. One is questions, and the other one is problems. The questions are usually concept questions, and I usually don't ask from there. And if I ever ask from there, I specifically say question, blah, blah, blah. But if I don't say anything, it's from the problem section. So the small block has a mass of 4 kilograms, and the large one has a mass of 1 kilogram. Okay, and what we want to find out is where can we put a pivot so the whole thing is balanced. Okay, so you can imagine that the large block is going to have a center of gravity at the middle, at the 1 meter mark. The second one is going to have another center of gravity that's also going to be at the midpoint of that block. So when we put them together, they're going to combine their centers of gravity, and then going to have a net or a total center of gravity. And we want that center of gravity to be where we put the pivot point. So basically, what they're asking is, where is the center of gravity of the system. Okay? And we actually have an equation for that. So the center of gravity is x1 m1 plus x2 m2 over m1 plus m2. Now, this center of gravity is what this problem is calling D. Okay? So that's the question that we're gonna use. Now, the other thing that we need is to set up a frame of reference. And you can place the frame of reference anywhere you want. So I'm gonna place my frame of reference at the edge, at the left side of the large block. Okay? But you can as well place it on the right side, or you can put it on the middle. It really doesn't matter. So, so with this frame of reference, the distance to the center of gravity, x1 is a large block. So x1 is the location of the center of gravity of that block. So this guy over here. So this will be 1 meter. The mass is 1 kilogram. The location x2 will be the location of the second center of mass, which that will be 1.5 meters. And the mass is 4 kilograms. And then you add 1 kilogram plus 4 kilograms. And that will give you the center of mass. Oops. Say that again?
1.1 meters, so that's mental math, so.
Oh. Yeah, good mental math. Okay, so 1.4 meters is the location of the center of mass, and you know that if you put a pivot point at the center of mass, the net torque will be 0. So that would be the location of the pivot point. Yeah, try to always do the problems. Usually I don't ask questions. Or I don't usually don't ask from the question section.
Okay, and then we just go over 53. I just need like a sense of direction.
53?
Mm-hmm.
Oh, I signed that one. A man is attempting to raise a 7.5 meter long. Oh, I must really not like you guys.
I thought you only did 50.
Well, no, that one is the same as the spine. It's actually the same problem as the spine.
That's the what?
53.
That's the first question we did.
Oh.
I'll do it. So problem 53.
Mine is really failing.
52?
Yeah.
Classic. Classic.
Okay, yeah, I didn't thought that I assigned 53 because 53, you can try to solve 53. 53 is exactly the same problem as problem 68, just with one less force and the distance changes, but it's exactly the same problem. Okay, any other question then?
66.
66 at the head? Okay.
Specifically the second one, per B.
Already, should I do all of them or just B? Oh. Okay. Trinity, thank you. Okay, so 53 is the head one, is the one with the head. That's my head. Okay, so in this case we have a center mass of the head. That's when the weight of the head is going to be focused, and that one is going to be close to the nose, at least according to the above the temple. And we're going to have at the pivot point is going to be somewhere around here, and then the muscle is going to be somewhere around here on the neck. So this is the weight of the head, this is the muscle, and this is my pivot point. And here I'm probably going to have a reaction force that I don't know where it is. Now I'm going to look at the distances. This is a problem that is very similar to when we're talking about the foot, and look at the ankle and the Achilles tendon is the same configuration. You have the pivot point in between the load and the force. So we're going to be solving this with a moment of arm. So what I'm looking for are the distances between the different forces. So the distance between the center of mass and the pivot point, this is going to be 4.2 centimeters. The distance between the pivot point and the force of the muscle, this is going to be 5 centimeters. And the distance between, and the vertical distance between the center of mass and the pivot point, that's going to be 10 centimeters. Okay? So if the person is standing up, and I want to know what is the force of the muscle, then what I'm going to have, I'm going to have a reaction force on my pivot point, and I'm going to have a force here, the force of the head, and I'm going to have the force of the muscle. And this distance is going to be 4.2, and this is going to be 5 centimeters. Okay, if I want the whole system to be in equilibrium, then I'm going to have all the torques equal to 0. Okay, I'm placing my frame of reference at the pivot point, so I don't have to worry about the torque created by that reaction force. And then I will have just a known of the muscle. That is the one that I want to find out. So I will have the torque of the head. That's going to be 0.042 meters times the force of the head. And the head has a mass of 4.8 kilograms. 4.8 kilograms times 9.8. And this one rotates counterclockwise, so it's going to be positive. This one rotates clockwise, so this is going to be negative. So, this will be the torque created by the head. And this one will be the torque of the muscle, and that one will be 0.05 times whatever force of the muscle I'm going to get, and this is going to be 0. There's an angle there, but the angle is going to be 90 degrees, so that's why we don't write it down. And from there, I can find the force of the muscle, 0.042 times 4.8, 9.8 over 0.05. And I got 39.5 newtons. Okay. If you say this is a configuration like a seesaw, you have the two gates on one side and you have the pivot point in the middle. Okay.
I just have a question for like the distances. I went ahead and just straight like scaled them both by the, like I scaled them up to where it was 4.2 and 5 instead of rounding, going back down to centimeters.
Oh, do you work with centimeters instead of with?
Instead of using like all the decimals, I just scaled it up, so
Oh, so you use 0.4 instead of.
4.2 and 5, so I just scaled it up.
Okay, so you work with centimeters instead of work with meters. That one will work here, but it will work. I think in this case it will work. I'll suggest that you always work with meters, especially when we start working with constants. You cannot mix constant with meters and centimeters. So it works in this case, but just create the habit of always working in meters. Okay, so now I'm gonna be doing the horizontal case. So now the person is gonna be laying down on his belly or her belly, and is gonna try to keep the same position of the head. So just keep the head straight. So this head, instead of being in this position, is gonna be like this. Okay, I'm gonna try to draw it. So, which should be too hard because it's just a circle. So I have, this is the nose, this is the eye, this is the center of gravity of the head, this is my pivot point, and this is my muscle. The muscle is gonna be pulling this way. But now gravity is gonna pull the weight in this direction, okay? And same thing, I want to know what are the distances. So the distance between the center of gravity and the pivot point is going to be the 10 centimeters. And the distance between the muscle and the pivot point, that's still going to be 5 centimeters. Yeah, everybody can see that one. So we still have the same equation. The sum of torques, oops. The sum of torques have to be equal to 0, okay? And so we still have two torques. We're still going to have the torque of the head plus the torque of the muscle has to be equal to 0. I'm still placing my pivot point at the joint, at that where that reaction force is going to be. The direction of the reaction force also changes when the person is laying down, but we don't care about right now about the reaction force, so we're not going to draw it. So the torque of the reaction of the head, notice it's still pointing down, so it's still rotating counterclockwise, so it's still going to be positive. This guy is still rotating clockwise, so this is still going to be negative. So I'm going to have it's 0.1 meter, no, 0.1 meter, so that's the 10 centimeters, times the weight, so it's going to be 4.8 times 9.8 minus 0.05 times the muscle is going to be 0. So that will be oops. I end up with 94 Yeah, 94.1 newtons. Yep. Yeah, Aubrey, Mother, makes sense? Okay. Any other question? Okay. Okay, so I know that many of you are athletes. They are in some kind of sports, and in any sport, at least I don't know one that doesn't. Uh, One of the basic exercises that you need to do is the squat. And there are different kind of squat, and each squat has some benefits or they have some advantage over the other ones. So you have the squat in which you put the barbell in front of your under your chin. You have the squat when you put the barbell behind your neck, and one where you put the barbell lower on your back. Okay, and one of the things that it causes that change in position of the barbell is that it's going to change the way you change your body or the way you do the way you do the squat. So depending where you put your barbell, the angle that your back is going to be doing with horizontal is going to change. So in one case, when you have the barbell in front under your chin, you have a more erect spine. If you have it somewhere in the middle of your back, your angle changes. Now, why does the angle changes? Well, because remember that you need to keep an equilibrium position. So you want the center of mass to be between your toes. If you don't change your position, you're gonna leave.
No, I'm just,
You're going.
no, I just.
We still have like.
I write my notes in pen, so
Oh.
I was putting my pencil away, but I do my homework in pencil.
Okay. You want the center of gravity to be above your foot. This is going to be your base. So if you don't change your position of the spine, if you don't change the position of your back, then the barbell is going to be outside this range, and you're going to fall and you're going to tip. Okay. The barbell in some cases is bigger than your body weight. So it is considerable and it's really high. So any changes over the vertical is really going to affect your balance. So this is one of the things that you want to do. Now, one of the things that you want to figure out is, okay, what is going to be the stress on your spine, or what is going to be the stress on your hips, or what is going to be the stress on your knees. By doing that, you can calculate what is going to be the muscles that are going to be activated the most. So is your quads, or is your glutes, or is your hamstrings? Which ones are going to be the ones that are going to be activated the most? Now, this angle that I'm drawing over here, this 69 or this 53-degree angle, these are really hard to measure in real life. Like you cannot, if you imagine that you are with a patient or you are in a gym with someone, these muscles, these angles are really hard to do. You will need to take a picture, and then the picture you can just look around and make sure that your camera is horizontal, is parallel to the ground. It's not that simple. Not impossible, but not simple. What you can do, however, is that you can take measurements of the patient beforehand. You can measure what is the distance between the neck and the hip. You can measure that distance. Or you can measure the distance between the position of the barbell to the hip. That's going to be a little more relevant. And then what you do is you can draw vertical lines. And just by gravity, you can put a plumb and just draw. And just look. Oops. just at the vertical of whatever the weight is. Okay? And then the distance that you care is going to be the distance between the joint that you want to analyze and that vertical line. So you're going to care about this distance. Yeah. Now, if Dylan, wake up. You've fallen asleep. The nerd. If you see the changes in distances, so I'm going to draw it over here. So this is going to be the distance between the hip, and this is the distance to the knee. Sorry, I think this is more like this. And this is not a good drawing. Okay, so here is a little more evident. So you can see how the distance or the moment of arm for the knee is smaller than the one from the hip. So this ratio changes. As this ratio changes, the muscle activation is going to be way different. So the torque, just because the moment of arms are different and the weight is the same, the torque on the hip is going to be much larger than the torque on the knees. And here you can see like, well, the torques are going to be a little bit more balanced on the other cases. I think this one is wrong, and this one the torque on the knees is significantly larger than, well, not larger, but it's a little bit larger than the torque on the hip. So depending on what muscles you want to activate, if you want to activate mostly the quads or the hamstring, well, maybe this position is going to be better. If you want to activate the glutes and the quads, this is going to be a little bit better. Okay, so that's why the position changes. So measuring this distance is a little bit relatively easier than measuring the angles. So this is one of the reasons that we work with moment of arms instead of working with perpendicular forces. So to calculate the torque, again, I'm going to calculate the torque on the knee. Okay. And I'm just going to look at the weight of the barbell, and I'm not going to look at the weight of the person, although you can consider also the weight of the torso. So the torque on the knee for this case is just the mass of the barbell. So it's going to be 100 kilograms times 9.8. And then the moment of arm is going to be 18 centimeters. So it's just 0.18.
And then K stands for what?
Sorry?
What?
What?
What is, oh, knee.
Knee. So this gives me 176.4 newtons meter. And in this case, it's going to be 100 kilograms times 9.8 times 12. And this will be 117.6 newton meter. Okay, so that's the torque on the knees. Like if you want to figure out what are the muscles there, or the forces on individual muscles, then you need to look at the insertion points of the muscles and what the muscles are being activated. But that will give you an idea, okay, do I put in too much stress on a knee or I'm putting too much stress on a hip, okay? Make sense? Ish? Any other questions for your exam? Anything? Alexis? Trinity? Jacob? No? Valerie? Aubrey, Mer, any questions? Yes.
Go over moment of arm.
So the moment of arm, let's say that I have this system. So I have a pivot point and I have a force over here. And I have this angle phi. And over here, this is a distance r. So the way we calculate torques so far is to say, okay, the torque is going to be this distance r times the perpendicular force. Okay, so for this particular configuration will be r times the force sine of phi. Okay, but there's another way that you can calculate the torque, and is to find the shortest distance between your pivot point and the force. So I'm going to extend this force and I'm just going to make this imaginary line. I'm going to find the shortest distance between the pivot point and this line. And that always going to make 90 degrees. So we call this moment of arm. You can see it also like the perpendicular distance, a perpendicular distance to the force. Okay, so the way we calculate the torque will be, okay, I'm going to do this perpendicular distance times the force. Now, how do I calculate this perpendicular distance? Well, if I have this angle phi, this is going to be the opposite to that angle, right? And the hypotenuse is going to be r. So r sine of phi will be the opposite, which is r perpendicular, and the hypotenuse is going to be that distance r. So r perpendicular will be r sine of phi. So r sine of phi times the force. So you can see that the two equations are the same. So the r perpendicular is what we call the moment of arm. Yeah, makes more sense.
Yeah, that makes sense.
Yeah, we're almost done. We're almost done. Any question? Alexis? Nope? No? Okay, so if there's no more questions, then let's stop here. If you have any questions, if you try to solve the problems, if you want to practice and you can send me an email, sorry, and I'll usually respond pretty quickly. I'll be here. I won't be here tomorrow. Again, if you want office hours or something, just send me an email and we can arrange something. Friday, I will be here at 8:30. So if you want to be in the classroom and you want me to go through anything, to do any last minute review, I'm more than welcome to do it. Okay? Have a good day and good luck on your exams.